Hi, this is Rami Yoon, and you're listening to the AP Bio lecture on water. You'll notice that with these lectures, we're going to be going over the more difficult concepts for each topic, and that means that if you need more of the basics, you have a few options before you come to this lecture. So you can go back to your ninth grade notes. You can skim through the textbook. You can listen to Bozeman science videos or Amoeba Sisters or Crash Course videos. And those will give you a better foundation in what this is all about. But with these lectures, we're going to be condensing down the topic into the most difficult parts. If you feel like this is going too fast for you, you can pause the video. You can look at the slides more closely on your own, or you can leave it, get a better foundation in the basics, and then come back to this video. You also can find these slides in our Google Drive folder, so you can print them out and have them next to you, or you can open them up and take notes as you listen. Our essential question for this lecture is, how does water enable the existence of life? And by the end of this lecture, you should be able to answer this question using all of these vocabulary terms. We're going to be talking about how hydrogen bonding gives water its properties, such as adhesion and cohesion, as well as temperature moderation. And we'll also discuss how water dissolves solutes to form solutions, which basically produces acids and bases, as well as buffer systems. I want to remind you to start out that the basic structure of an atom has positive charges on the inside and negative charges on the outside, and they're attracted to each other because opposites attract. But not only are these electrons attracted to protons in its own nucleus, electrons will be attracted to any positive charges that are just like near it or close enough to attract it. And so that's what we see with water. And once again, if you feel like I'm going through these slides too fast and you want to pause the video so that you can read the text, you can absolutely do that at any time. But most of this lecture is going to be focused on the pictures in the slides content. So here we have 5 water molecules, and you can see for each one there is an oxygen in red and there are hydrogens in white. And what I want you to notice is that every red oxygen has this little symbol. It's the Greek letter delta with a little minus sign next to it. So this oxygen atom is delta negative. This one here has the delta negative symbol next to it. This one here as well has the delta negative symbol next to it. And then even though they're not present in the picture, this oxygen is also delta negative. This one is also delta negative. You'll notice that the hydrogens have this symbol here. It's the Greek letter delta with a little plus sign. And so that tells you that the hydrogen atom in the water molecules are delta positive. In other words, they're slightly positively charged. This one is delta positive. This one is delta positive. All of them are delta positive. Last of all, you'll notice that there are these dotted lines in between the delta negative oxygens and the delta positive hydrogens, and these are called hydrogen bonds. Here's why. It's because oxygen atoms have 8 protons in their nucleus, so their nucleus has a +8 charge. Hydrogens have 1 proton in their nucleus, so they have a +1 charge. The electrons that are in the covalent bond between an oxygen and a hydrogen, so you can see that right here. See that line between the oxygen and the hydrogen? There are 2 electrons in that bond. Those electrons are not equally attracted to the hydrogen and the oxygen because the oxygen is more positive. The oxygen has more protons. And so the electrons in this bond are going to be pulled towards the oxygen. Now that the oxygen has more electrons around it than just its own, that's going to give the oxygen atom a negative charge. We call the oxygen delta negative. It's slightly negatively charged. So it doesn't have a full ionic charge, but it's not neutral either. And then because the electrons in this bond are not pulled towards the hydrogen, they're pulled away from the hydrogen, that means that the hydrogen becomes less negative, which means it becomes more positive. And so this hydrogen atom has a delta positive charge. And as you know, opposites attract. So this slightly negative oxygen on this water molecule will be attracted to the slightly positive hydrogen on this water molecule, and they'll form a temporary weak attraction that we call a hydrogen bond. Where a hydrogen bond is any bond between a hydrogen atom on a molecule that has an electronegative element like oxygen and some other electronegative element on some other molecule. The term electronegative, you'll learn it in chemistry if you haven't already done so, but the term electronegative or electron affinity refers to how attractive are atoms to electrons that are nearby. So we have multiple hydrogen bonds present among these four water molecules. Each of them is weak on their own, but because water has the capacity to form so many hydrogen bonds, together they're actually really strong and they allow water to do some amazing things. In fact, because of water's ability to hydrogen bond, it can do all of these things, and we'll go through them one by one. The first is cohesion and adhesion. Cohesion is water molecules' ability to bond, hydrogen bond with each other. And adhesion is a water molecule's ability to hydrogen bond with some other hydrophilic substance. So here's an example of that. You can see this tree has its roots underground, and when it rains, the rain soaks into the soil. So the soil is going to have a high concentration of water. When the sun comes out, the sun is going to cause water to evaporate from the leaves. And so water is going to be pulled up through the roots, it's going to go up the trunk of the tree, and it's going to escape into the air through the leaves, which is weird because that means that the water is moving against gravity. But there's a couple of things going on here. Not only is water moving along its own concentration gradient, because remember, high water concentration at the roots, lower water concentration at the leaves, and like all diffusion, water moves from high concentration to low concentration. But on top of that, water is able to literally climb up the trunk of a tree because tree trunks have these pipes. You can see a cross section of the tree. So there are all these little pipes that go up the entire length of the tree trunk. And these pipes are basically made of hollow cells that have these big gaps in between them. And water molecules hydrogen bond with each other, cohesion. They also hydrogen bond with the cellulose in the cell walls of these pipes. And so that allows them to, anchor themselves to the cell wall and then climb over the next water molecule and then anchor it and then climb over the next one. And so water molecules can climb over each other up and up and up a tree. Here's another example of how water is able to do amazing things because of its ability to cohere together or hydrogen bond together. Here you can see this water spider is able to walk on water because any body of water is going to have a surface, and the surface molecules, the surface water molecules, are going to hydrogen bond with each other. And because the spider is able to distribute its weight across all 8 of its legs, these legs will not produce enough force to break through the hydrogen bonds that are holding the water molecules together. And so that's called surface tension. The spider is able to walk on water because it does not break the surface tension or the hydrogen bonds between the water molecules. In addition to that, water is able to moderate the temperature of the atmosphere, of organisms, of like ecosystems because of its ability to hydrogen bond. So what's happening is anytime that the temperature goes up, what that means is there's a lot of thermal energy in the air. Thermal energy is going to basically cause water molecules to have more kinetic energy. So they're going to basically vibrate more. And as they vibrate more, that causes hydrogen bonds between them to break. When you have the thermal energy basically transferring into the water or out of the water and causing water molecules to move around and break hydrogen bonds or form new hydrogen bonds, that thermal energy is being transferred, and we call that heat transfer. I know that was kind of complex, and this is a physics concept that is applicable to biology. Do you need to understand the physics and the chemistry that underlies this? No. What you do need to understand is that heat can be transferred from one body of water to another, or from one organism that has water to some other environment. And so the reason why water is able to do this is because the hydrogen bonds in water give water a high specific heat. You can see the definition for specific heat here, but basically the idea is the higher the specific heat of a substance, the more heat energy or thermal energy you have to add in order to cause that substance to evaporate, or in order to cause that substance to change its temperature. If you've ever watched a pot of water boil, you know that it takes a lot of heat. You have to just add a massive amount of heat into a pot of water before you change the temperature enough to allow it to evaporate. And that means that water is able to absorb a lot of heat before it starts evaporating. In fact, because water has so many hydrogen bonds, the water can absorb a lot of heat as those hydrogen bonds break. And then the water can release heat as hydrogen bonds reform. So here's how that's significant to life. You can see that this is the coastline of Southern California. Santa Monica would be somewhere around here. Redondo Beach and Palos Verdes are somewhere around here. And we're near the ocean. And so because we're near the ocean water is going to absorb heat from the sun during the day, which means that it becomes less hot along the coastline. And then at night, the ocean, is going to release heat back into the atmosphere, which warms the air around us, and that keeps our nights pretty, not too cold. You can contrast that against the inland empire. So in the day, especially during the summer, the inland empire, so that means areas like San Bernardino or Riverside or Palm Springs, they're going to typically be at least 10 degrees, but usually closer to 20 or even 30 degrees hotter because they do not have water nearby to cool them down. And then at night, the inland empire is typically at least 10 degrees colder than it is along the coast. Their summers are really hot. Their winters are really cold, and that's why beach cities have much higher property values. Homes are much more expensive because when you're near the water is going to exert what we call evaporative cooling during the day, and then warming at night. And you can see the definition for evaporative cooling here. Here's another example of that. If it's a really hot day, you sweat. And as you sweat, water beads up on your skin. And so as the heat from your body causes the hydrogen bonds to break in the water in your sweat, that sweat evaporates, and that takes the heat away from your body. And so your sweat is evaporatively cooling your body off. Another example of how hydrogen bonding in water moderates temperatures is the ability of living things to live even in frozen lakes. So what's happening here is this is liquid water, and you can see that it's forming these hydrogen bonds and they're breaking and reforming just kind of willy-nilly. But as the temperature drops, then the water molecules don't move around as much, and as they slow down, that gives them time to form the maximum number of hydrogen bonds with neighboring water molecules that they can. And so they form these crystalline structures that trap pockets of empty space between them. And that actually causes the water molecules to be farther away from each other than they are in liquid water. In other words, ice is less dense than liquid water, which causes ice to float on top of liquid water. And when that happens, the ice that forms on the top of a body of water will actually insulate the water underneath, or in other words, it keeps the water underneath from losing more heat. And so that allows life to continue even in a lake that has frozen over. Next, because water is able to hydrogen bond with all sorts of things as long as they're hydrophilic, that means that water is what we call a great solvent. So a solvent is something that can dissolve a solute. A solute is anything that can be dissolved. And if you dissolve a solute in a solvent, then you have what's called a solution. If the solvent is water, so in other words, if you're dissolving something in water, then it's called an aqueous solution. And an example of that is salt water. So if you dissolve salt in water, you have a salt water aqueous solution. Here's a salt crystal. It's got these negatively charged chloride ions and these positively charged sodium ions, so NaCl, table salt. And as you can see, if you're a negatively charged chloride ion, guess what's attracted to you? All of these little delta positive or slightly positive charged hydrogen ions in the water molecules. If you're a positively charged sodium ion, guess what's attracted to you? All of the delta negative oxygen atoms in surrounding water molecules. And so these water molecules will completely surround a sodium atom and pull it away from its crystal. And similarly, they'll do that to a chloride ion and pull it away from its crystal. And so eventually the crystals will dissolve to the point where you can't even see them anymore. And at that point you have a homogeneous aqueous solution. Here's another example of that. So this purple thing is a protein. And it's got some hydrophobic and hydrophilic regions, but all of the hydrophilic regions will be on the outside. And so what is a hydrophilic region? It's any region that has positive and negative charges, because the positive charges will be attracted will attract the oxygen side of water molecules, and the negative charges on a protein will attract the positive side of water molecules. And so all these water molecules just completely surround the protein and stick to it, and they form what we call a hydration shell. Hydration meaning, water. And then shell because they're literally forming a shell of water molecules around this protein. And so they're dissolving the protein. They're making an aqueous solution. Just keep in mind that only hydrophilic substances can dissolve in water. Hydrophobic substances are not able to dissolve in water, and examples of those are lipids. And we'll talk about lipids at a future point. Okay, next, you guys need to know that solutes, the things that dissolve in water, if as you add more solute into an aqueous solution, you're increasing the solute concentration. And water itself can act as its own solute. So here you can see we've got two water molecules. And in this case, this negatively charged oxygen atom could just form a hydrogen bond, or it could actually steal a hydrogen atom away from this other water molecule. If that happens, here's what you get. You get a water molecule that has 3 hydrogens, not 2. And you get another water molecule that only has 1 hydrogen. But when this water molecule lost the hydrogen, it actually kept its electron. Because remember, the electrons in that bond were more attracted to the oxygen. So the electron will stay with the oxygen, which means that the hydrogen that it lost, remember, a hydrogen is just a proton and electron. So since it left its electron behind over here, this hydrogen is just a proton. It's just a positive charge. And so that causes this entire molecule to be positively charged. We call this a hydronium ion, and its symbol is H3O+. We call this one a hydroxide ion, and its symbol is OH-. By the way, this is a reversible reaction. So you could have one water molecule stealing a hydrogen from another to produce a hydronium ion and a hydroxide ion. But also you can have a hydroxide ion because of this negative charge, stealing the hydrogen ion back, and if it does that, then you just have water molecules again. You guys need to know that this hydrogonium ion can also easily dissociate or break down to just form a water molecule and a hydrogen ion again. And if it does that, then basically we say it's increasing the hydrogen ion concentration in the solution. So we're going to use the terms hydrogen ion and hydronium ion interchangeably. By convention then, H plus is used to represent a hydronium ion, where remember H plus is just a hydrogen ion that's lost its electron, or in other words, it's just a proton. And we're going to use those terms interchangeably. Hydrogen ion, proton, hydronium ion. For this class, those all mean the same thing. So here you can see in this beaker we have a high concentration of hydrogen ions compared to hydroxide ions. A lot of H pluses compared to OH minuses. We call this an acidic solution, where the concentration of hydrogen ions is greater than the concentration of hydroxide ions. Contrast that over here with this beaker, where you have a low concentration of hydrogen ions compared to hydroxide ions. And we call that a base. A base is a solution, an aqueous solution, where the hydrogen ion concentration is less than the hydroxide ion concentration. Now, if the two are roughly the same, we call that a neutral solution. And an example of a neutral solution is pure water. If you know about pH, then you know that the pH of pure water is 7. Anything that is acidic is going to have a pH less than 7. So battery acid has a pH of 1. Lemon juice has a pH of around 2. And blood has a slightly basic pH. It's like 7 point, I forgot what it is. Here you can see that bases have a pH higher than 7. So bleach, for example, has a pH of 13. The higher the pH, the more basic the solution. The lower the pH, the more acidic the solution. Here's another way of saying that. The lower the pH, the higher the concentration of hydrogen ions. The higher the pH, the lower the concentration of hydrogen ions. There is an inverse relationship between the concentration of hydrogen ions and the pH. And the reason why is because of the way that we calculate pH. So pH stands for power of hydronium ion, or power of hydrogen ion. And here's its definition, right here. You do not need to memorize this formula because it is on the AP Bio reference sheet, but you do need to know how to use it. If you want to know the math behind it, I'll explain it briefly. And if you don't understand my explanation, that's okay, because as long as you can understand the shorthand relationship, that's good enough. But basically, if you really want to know, as a mathematical expression, you should know that an equal sign stands for is represented by the word is. The logarithm refers to the power or the exponent that you put on the number 10. So this log has a base of 10. And so when we read this mathematical expression, it basically is saying that the pH is the negative power that you put on the number 10 to get the hydrogen ion concentration. So if you take a look at that bottom bullet, okay, now it's not covered by the navigation bar anymore, but look at this expression. So I'm going to read it from left to right. The negative power that we put on base 10 for the hydrogen ion concentration is negative, I'm garbling it, but basically, let me try it another way. Here, if you have a pH of 7, what that means is that the hydrogen ion concentration is 10 to the negative 7, which means that out of every 1 million molecules in the solution, one of them is going to be a hydrogen ion. Over here, this is a pH of 1. So what that means is the hydrogen ion concentration is 10 to the negative 1. In other words, out of every 10 molecules in a solution, one of them will be a hydrogen ion. Another way of saying that is 10% of the molecules in a solution of battery acid is going to be hydrogen ions. So the higher the hydrogen ion concentration, the lower the pH. So when we look at the pH formula then, just remember that the pH is going to be the negative power that you put on 10 to get the hydrogen ion concentration. Last of all, buffers are basically solutions where you have substances in there that can either donate hydrogen ions or that can reduce hydrogen ions in solution. I skipped a step. You guys should know what the definition of an acid and a base is. An acid is any substance that increases the hydrogen ion concentration in a solution. So if you have an acid, you're going to have more hydrogen ions in solution. A base is going to be any substance that reduces the hydrogen ion concentration in solution. And so a base will cause there to be a lower hydrogen ion concentration in solution. So a buffer is going to have substances in there that can act as both acids and bases. And an example of that is carbonic acid. So here you have basically hydrogen bicarbonate, H2CO3. And when you add that to water, it can either release a hydrogen ion, in which case you have what we call the bicarbonate ion, HCO3 minus, hydrogen bicarbonate, and it will also produce a hydrogen ion. So you can see that this releases a hydrogen ion in solution, so it acts as an acid. But this is also reversible. So this hydrogen bicarbonate ion can actually accept hydrogen ions to reform H2CO3. And so because of the presence of both this molecule and this molecule in solution, this is what we call a buffer system. Here's why that's significant. So a great example of a buffer system in action is ocean water. Here you have a plane shooting by across the sky, and as the plane runs, it's going to release massive amounts of carbon dioxide into the atmosphere. The carbon dioxide will actually get absorbed into the water. So some of the carbon dioxide gas dissolves into the water, where the carbon dioxide molecules react with water to form H2CO3. That H2CO3 can then break down to form hydrogen ions and bicarbonate ions, which means you've now acidified the ocean. The ocean is now becoming more acidic. Fortunately, the ocean itself is a buffer system. And so what's happening here is these are coral reefs, and they're made of shells that basically are made of calcium carbonate or lime. So these carbon-containing shells can actually break down to form calcium ions and these carbonate ions. These carbonate ions can then interact with hydrogen ions in the ocean to form the bicarbonate ion. And so while on the one hand you have carbon dioxide that's acidifying the ocean here by producing hydrogen ions when they react with water, you also have these carbon shells that can interact with the hydrogen ions to form bicarbonate, which then reduces the acidic content of the ocean, keeping it neutral and basically buffering the harmful effects of carbon dioxide. However, because of human activity, all of the industrial activity and shipping and other things that we do, all of the carbon dioxide that we release into the air, we're actually acidifying the oceans faster than they can be neutralized by this natural buffer system. It's actually breaking down the coral reefs and causing them to bleach or die out. And that's endangering the stability of our ocean ecosystems. And that's something we're going to talk about more when we get to our ecology unit. Okay, here are your key takeaways. So first, you should remember that water molecules form weak bonds called hydrogen bonds because water molecules can cohere to each other and they can adhere to other hydrophilic substances. And so for that reason, water has many properties that sustain life. Hydrogen bonding in water also means that water has a high specific heat, so it can store and release a lot of thermal energy. You also should know that water molecules interact with solutes to dissolve them, which means they form aqueous solutions. And that means that they can have a pH. If an aqueous solution has a high pH, a high hydrogen ion concentration, they will have a low pH, and those are acids. Aqueous solutions that have a low hydrogen ion concentration, which is the same thing as saying they have a high hydroxide ion concentration, they have a high pH, and we call those bases. And if aqueous solutions have solutes that can both donate and accept hydrogen ions, then they're going to minimize changes to hydrogen and hydroxide ion concentrations. So they have a relatively neutral pH, and we call those buffers. But you should remember that carbon dioxide dissolves in ocean water to create a natural buffer system, but because of increased carbon dioxide emissions from human activity, we're acidifying our oceans, and that's destroying the ocean's natural buffer system. I know that was a really dense lecture, and basically, if you can master this content, then that's going to give you a really solid foundation for future biology topics that we'll be going through in this course. Before you guys leave, I want you to pause the video and just see if you can answer this essential question using these vocabulary. If you can, that means you've mastered this topic. And if you can't, then you should identify which of these vocabulary words you're not sure how to use. And then that should guide you in terms of what are you going to study further in order to prepare for the unit test.